Hi, we're back with another video from Ozen Engineering. My name is Hatem Akal. I'm going to talk today about NuHertz, a filter design tool from ANSYS. NuHertz is another tool available with the electronic desktop from ANSYS. It's a powerful filter design tool. The interface is simple and easy to learn, and there are tens of designs you can choose from. Here is the NuHertz tools interface. You can see we have a lot of options. In order to use this tool, you need to have some background on filters. NuHertz won't tell you what to pick. At the top left corner, we have 4 band options: low pass, high pass, band pass, and band stop. In today's example, we choose band pass. And here we have the different patterns: Bessel, Butterworth, Chebyshev with ripples in the pass band, or Chebyshev with ripples in the stop band. And also we have the elliptical, which has ripples in the pass band and its stop band. You need to know about these types, their advantages, and which one is the right one for your application. It doesn't matter what you gain by using any of them. You will lose something else. We picked the first kind of Chebyshev filter for today, this one. You can design lumped filters, distributed filters, active filters, switch capacitors, and finally digital filters. For example, if you choose the distributed one, NuHertz will fill up this box with many topologies. Think of them as extra requirements. In our case, we will choose the compline one. On the right, we have the substrate definition. NuHertz needs this information to do the right calculation. You can click it, select your transmission line. In this case, we selected microstrip. And depend on what you select, the substrate parameters will change. We will go with microstrip. If we want, we can add a cover. We need to tell the software what is the conductor thickness and the dielectric thickness. We need also to know what materials to use with the microstrip. So you can select for the conductor a gold or any one of these materials. Notice that the numbers are relative conductivity with respect to the copper. So copper is 1, gold is 1.43. Now it's okay if you can't find your material. Choose the one that's the closest. Later on you can change it. You also need to select the dielectric. Same thing. Try to select something from the list. If you can't find it, select the closest one. Notice here that with each one of these materials, there is a specific loss tangent that comes with it. You can select to modify that and enter your own value if you want. Save and close. The next step is to fill up these 2 tables. In the second table, you have to enter the center frequency of the passband, which is at 1 GHz in our case. You need to enter the bandwidth of the passband, which is 200 meg, which is 100 meg on each side. You also need to specify the stop band bandwidth, 400, which is 200 on each side. Now, in our definition, we selected the center frequency definition. You can also select the band edge definition instead. In the first table, you need to specify the allowable ripple in the passband. You need to specify the attenuation at the stop band, which we said it's 400 MHz, 200 on each side. You need to specify the impedance of the lines. Now, because of the manufacturing tolerance on a PCB, you need to provide the manufacturing design rules: minimum line width and the minimum gap, of course. Don't try to pick up the minimum. That will make your design really sensitive. Remember that the dielectric thickness in any design is selected so that the impedance of the RF lines doesn't change more than 10% with the worst manufacturing tolerance. You can also set a maximum for the width and maximum for the gap. Just select a big number, but don't allow it to be infinity. Like, put some numbers there. Based on the numbers you give, the software will choose the order of the filter, but you can impose the order. You can force an order if you want here. Add TX zeros if you want to flatten the phase of your filter. Usually we add zeros to the TX in order to flatten the group delay. And the last thing is asymmetric. You can select to have a non-symmetric filter. Notice here that the moment you select that, the whole setup changes. We will talk about that in another video. Here is the design window. We see a sample of the filter in the design window. The filter length, the width of each tuning stub, the gaps, and also the capacitance of each stub. We can also see the tap points where the input RF line connects to the first stub. The output, the same thing. We can print this to a PDF, OneNote, or OrCAD. So we have few options here. You can also copy to clipboard, then paste it somewhere else into another application like PowerPoint, Paint, or Word. We can create a netlist. We can do Monte Carlo, and we're going to talk about it later on. We can also annotate. You can write something here. You can also edit your filter, edit all these numbers. You can see the layout. You can see it also in 3D. You can specify here how many digits in each number. For example, here is 4. So you see here we have 4 digits in each number. You can have more. You can use fit in order to fit the whole filter in your screen. Sometimes when you select this option, you won't be able to see the numbers. So you prefer to go with unfit. If you select other information, then instead of seeing some dimensions, you will see impedance, the impedance of the stubs. And this is the coupling impedance between each stub and the next one, or the adjacent ones. We come now to the results window. It shows the S parameters of the filter. The group delay, if you want to see the group delay. It can show it in linear frequency or in logarithmic frequency. This is logarithmic. This is the x-axis. You can automate the min-max, or you can control that if you want. You can print it, same thing like here. You can copy, and you can specify the limits of the y-axis. If you click here, I can specify the max and the min of S21 or S11. This is the y-axis. Number of division, controlling the display. You can also see the numbers in text format. So that's the frequency, and that's the amplitude of the S12, and this is the amplitude of S11 in dB. You can also zoom. This is for zooming. This is for moving left and right, and here to restore back to the center. You can display S12 and S11, or you can say, I just want to see S11. The base that you see here in blue is the response of the filter if the Q is infinity. There are no losses. You can plot the results in dB. You can plot them in absolute magnitude. You can plot Smith chart. You can plot it in polar. So you have so many choices here. If you click the right button, you will get a marker. If you click on the marker, you can modify its X location, at what frequency you want that marker. Back to Monte Carlo. Here you can select to update the width of the stub and also the gaps, update the length. You can also update epsilon r if you want. Here you can enter the maximum tolerance, that's the manufacturing tolerance, and how many trials you want the software to try. You can have uniform distribution or Gaussian distribution. The Gaussian just focuses on making small changes instead of big changes, or more often than big changes. You can select to maintain all traces in case if you are repeating the Monte Carlo many times. You can record all the results or just the final one. Now we come to the most important part, which is exporting. You can export the results, an S parameter, Y or Z touchstone file, export the design to a DXF AutoCAD file. Now, you can also export it to ANSYS electronic desktop. And to do that, you need to do some setup. And this is the setup. You can select to send the design to circuit, or HFSS design, or HFSS 3D layout. You can also ask the electronic desktop to simulate after exporting. And you specify here which parameters you want it to solve. You can ask for S parameters, group delay. These ones, they are not applicable here. In the S parameters and group delay, you specify you want the input return loss, the forward transfer. And you want the report to be in a rectangular format. You could select Smith chart, you could select polar plot, table data. If you want to do optimization, so you activate this, you can ask it to start the optimization immediately after exporting. If you don't, then NuHertz will do the setup for the optimizer, but it will not run it. And if you select to do optimization, then you need to fill up this form, which is the frequency, the goal, what do you want. Yeah. You can select to go full parameterization, which means it's gonna parameterize all the dimensions and solve for them all. There are other stuff that you can specify, which is the side boundaries. Do you want them to be radiation, or you wanted this filter to be enclosed in a metallic enclosure? You can also specify how much the substrate geometry extends beyond the metallic region. So you can add a buffer, or you can stick to the absolute value. You can here specify if you want NuHertz to create directly the model in the electronic desktop, or create a Python file. Then you can run that Python when you are in the electronic desktop. It's highly recommended to choose this option, so you will learn programming of Python with ANSYS electronic desktop. You can save and close, or go back to the default configuration. You can cancel all the changes. And you can also append to ANSYS desktop. You can override to ANSYS desktop. By the way, we can also automate port tuning options. You can allow that. So we'll get more options. There are still more options here that we're going to talk about them in another video. Close this window. Back to export. Now we finish setting up for the ANSYS electronic desktop. Now we want to do the export, and you can, as you can see, you can generate the Python file. The last thing is the setup for the 3D data. This is a generic 3D file that can be used in lots of applications. It creates a text file. User can read this file directly into other applications, or write a script to do it, to allow other applications to read it. In this video, we cover a lot of things related to the NuHertz interface. In future videos, we will be talking about more options that exist that we didn't talk about them, and about different kinds of filters and different options in terms of the band or the shape. Thank you for listening.